Well, hi, class. I think you're going to love this section. So we just did derivatives by hand, and that is the definition of a derivative is the limit as, the function is going to like one more with the full method that we did with the four-step process. So now we have these patterns that allow us to kind of do a derivative a lot faster. And so we will study, this one's the basic one, and it is amazing. We will study these ideas for like a whole chapter. So thank you, Newton, like for coming up with some shortcuts and some patterns. I think it was Newton. All right. Um, Here is the top of the section 9.5. Couple things is that derivative symbol can be a little bit different, right? We can do the little prime right here. We can do y prime on, so function notation y, or we can do dy dx, change in y over change in x. All of those are acceptable derivative notation. And then it gives us our theorems here. And it's basically saying the derivative of a number of a constant is always 0. So the derivative of any constant is always 0. Okay, and then the next kind of shortcut rule that we're going to love is that you can, when you have a power, you can bring that power down front, and subtract one on your exponent, and that's the derivative. Okay, so again, we bring the power out front, subtract 1. Amazing, right? This is going to change, game changer right here. So, and you'll see in our problems. The next one says you can take the constant out and times by the derivative. So basically, like if I have 3x to the second, I can keep the 3 out front, do the derivative, and then times anything I need to on the front. So basically, you just keep that power, that constant number there. Okay, last rule is you can do the derivative in between each plus and minus sign. Again, that's amazing. So let's do some way quicker derivatives. Look at this first one. We just have x to the 5th. So our rule says bring the exponent out front. So to do the derivative of this, we're going to bring the exponent out front, and then it's going to become x to the 5 minus 1. So really we have 5x to the 4th. So we brought the 5 out front and we subtract 1 from the exponent. Okay, or you could do the long way. I had one student once who missed the lesson on this section, and he literally couldn't remember the power rules, what we call this, or product or exponent rule kind of thing. And he did them all with the limit method. It took him forever, but that we like this rule. Okay, so we're going to start to write some things as an exponent so we can use our rule because we don't want to do the limit method. So we're going to look at this and we're going to think that's the same as x to the negative 4. Then I can take the derivative of that. They want me to label this one dy dx, change in y over change in x, which is totally fine. So whether it's a negative exponent, you still bring it down front. So negative 4, and then minus 1 from negative 4 is going to be a negative 5. All right, we could then move that back to the denominator if we want. This is an acceptable answer, but this is the same as leaving the negative 4 up top, and the 5th power on the x, right, becomes positive on the bottom. So I only move the x because it has a negative exponent. The negative 4 is an exponent of 1, so we leave it on the top. So these are equal, and your textbook in my math lab, your publisher allows both ways. Okay, but you should know both exist. So if I write something like this as the answer, you should know these match. That should be something you know. All right, so what if well, first of all, this wrote it a little bit different. Notice the y is missing on dy dx or dy du, and now u's are x's, which is why there's a u here. Really, it's saying d, and this is the y, du. So a little bit weird notation there. And we can write, gosh, how would we want to write that? I don't know. We could just do the derivative like this. To me, it doesn't really matter how you write that derivative piece. We could write it dy du. Yeah, I was trying to think what they were looking for, but I can't think of it. Okay, so then we're just doing the derivative. And what's so cool is we could do the derivative between each plus and minus sign because we had a rule that said that's allowed. So look at 2u to the second. Now you have a number in front, a 2 in front. So the rule says I can keep the 2 in front and then times it by the taking care of the u piece. So that brings down the 2. 2 minus 1 is going to leave a 1. I don't have to write that, right? So that's our first term. Then the second term, what happens if you have a 1 and you minus 1? You get a 0. So the second term, oops, I put an equal instead of a minus. The second term is going to be minus 3 times 1 because that anything to the 0 power is 1. So basically, if you just have an x or a u, it goes away, which is super handy, and we just have the number in front. Okay, and then 8 is going to go to 0. All numbers go to 0. So we can write this as 4u minus 3. So I can look at this and go 2 times 2 is 4, 4. 2 minus 1 is 1, 1. And this will drop off. So I have -3, -3, and the 8 goes to 0. Okay. Same idea on 4, except for 4, it's got some decimals. Totally okay. So derivative is going to equal 3.8x. 3.8 minus 1 is 2.8. Okay. And then 6 times 2. I can times the 1.2 down to the 6. So that's going to be a positive 7.2x. And then 1.2 minus 1 is 0.2. What does the -8x become? Just -8. What's the 2 become? 0. I don't have to write it. That's it. So notice we drop down 1 degree each time as we take the derivative. Okay, so problem 5 brings in the one that's the bigger deal to me is right here. Brings in that square root. How do I write the radical, any square root of x, right? How do I write that as a exponent so that I can use my exponent rules? Well, we wrote this as x to the 1/2. Okay, so if you have a third root of x, it would be x to the 1/3. Okay, if you had x to the 4th, well, let's do a 5th, something weird, something like this, right? And it's just a regular square root, but you have a 5th power underneath. It's going to be x to the 5/2. Right? If there's a power on the letter, you can put that as your numerator. So that's just a little reminder of that. So when I look at what I have, I want to rewrite all of this inside as the first one. I want to write it to the -4 because it's in the denominator. I need it to move to the numerator. So it becomes -4. And then plus, this is going to become 6x to the 1/2 power. And then the rest is already written pretty. So you have to write them prettier so that you can use your power rule. Okay, so now let's take the derivative. -4 comes down out front. I minus another one from -4. It goes more into the negative, so -5. Okay, 6 times 1/2. What's 1/2 of 6? 3. So x to the 1/2 minus 1/2 is -1/2. Or did I say that right? 1/2 minus 1. I said 1/2, whatever. 1/2 minus 1 is -1/2. So, and then this -5x becomes -5, 8 drops off. So we can rewrite this one, -4 over x to the 5th plus 3 over the square root of x minus 5. You should know both of those answers are correct. I don't care which way you write them. Both are great. Okay. Sometimes it's helpful to go back to a square root when if you have to put numbers into something, but you can do a -1/2 power on your exponents. It works. Actually, I have a TI-89 and I hate it because of exponents and I can't ever find The keys, this is so many functions on that calculator that I use the 1/2 a lot and 1/3 and things like that, just to find the third root and square roots. Okay. I don't think we need to do 6. It's just, we'll do it. Fractions are going to get people, so I'll just do it. Although I'm like, it's the same thing. Okay, so let's go ahead and do the derivative with some fractions. All right, so right now we have 7/5, so 7/5 is going to come down out front, and then you're going to have x. What is 7/5 minus 1? Well, 5 make a whole, so you're going to have 7 minus 5, or 2/5 left. If you can't do that, you go 7 divided by 5 on your calculator minus 1. And then you can go to math, that fraction, and you can convert it back to the 2/5. Don't care. Okay, plus 3 times 4/5. So think of it as 3/1 times 4/5. So that's going to be equivalent to 12/5. Okay, so we would have 12/5. Because 3 times 4 is 12. X, and then 4/5 minus 1. Well, 5 make a whole, so I'm going to be at negative 1/5. So I can go in my calculator, 4/5, 4 divided by 5 is 4/5, and minus 1, and I get negative 0.2, which I could then convert if I don't know that that's negative 1/5. Okay, and then this one's going to become a positive because you're going to have a negative times a negative. Negative 2/5 times 3 is positive 6/5. Right? Because negative 3 times negative 2 is 6, and the denominators are 1 and 5 that you times together. And then x to the, okay, so negative 2/5 minus 1, 5 make whole, so 5 plus 2 is 7. So I have negative 7/5. And then the 8 just drops off. Okay, if you can't do fractions as good as me, I don't care. I'm actually not that good. But I always think of whatever the denominator is. So these ones were 5. That 5 of them make a whole. So if I'm taking off 1 whole, I'm taking off 5. Right? So think about pizzas. If I'm going to take away a whole pizza, it's going to be all the slices, all 5 slices. All right, so number 7 says find the slope, find the equation. Okay, so we're going into, and where is it? Horizontal. We're going into some of these ideas that we learned about derivatives, like writing the equation of the tangent line, but now that derivative piece will be quicker. So this one first says, what's your derivative? Well, this is going to be a lot quicker to do our derivative on this one, right? So 2 times 7 is going to make 14. So 14x minus 9, right? Because the x will disappear and the 2 disappears. This is my derivative. This is my function. Part B says, find the slope of the graph at x equals 3. Well, what gives me the slope? Slope and derivative go together, right? So slope and derivative go together. So I can put the 3 into my derivative function. 14 times 3 minus 9 is 33. Okay, so that one ends up being 33. C says, find the equation of the line at x equals 3. So if we're trying to find the equation of the line of this one, remember we need the slope, which B made us find, and we need a point. So for C, we need the point, and we use the original function at that same value. So that value that we're at, we put into the original to get where we're at on the graph, and we put it in to get the slope of the tangent line. So we put that same value in the original and the derivative. One gives us the slope, one gives us the point. So this would be 7 times 3 squared minus 9 times 3 plus 2. I'm going to have to put that in my calculator. 7 times 9, because 3 squared is 9, minus 9 times 3 plus 2. I get 38. So our point is 338. Then we want to do our equation of our line. So remember, we go y minus y. So y minus the y value on my point equals slope times x minus the x value. Done. That's the equation of the tangent line. Yes, I could simplify it, but why? I'm lazy. Leave it. Done. I can distribute this. I can add this over. Depends on how it asks for your answer. My math lab will take this as your answer. Okay, problem D. D says, find the value where the tangent line is horizontal. Okay, tangent line, right? You're touching that graph in tangent line. Where would it be horizontal? Think about which type of line has, or what is, what is the slope of a horizontal line? 0. So if I want to find where x is when you're a tangent line, it's really where the derivative equals 0. So I was trying to get you to think of, but I did not say that well, right? Because what's the slope of a tangent line? 0. So the derivative tells us the slope. So I can look at the derivative and where it equals 0 if I want to find the values where the tangent line is horizontal. Okay, so that might be something you add to your note card. Just hard to remember. So our derivative was 14x minus 9. Where does that equal 0? And that's going to give me the values of x where the tangent line is 0. So I can add the 9, divide by the 14. I get 9/14 is the value of x where the tangent line is horizontal. Whoosh kaboosh. Okay, so this next one's the same idea, but this next one uses physics. So if you took straight Calc 1, you're going to do a million of this type of idea, and even harder because you'll use trig, and we don't use trig. Okay, 8 says, if an object moves along the y-axis marked in feet, so feet, y-axis, so that the position in time is your x, is indicated by the following. The instantaneous velocity of the function is equal to the derivative, which instantaneous derivative, we should think that way. The velocity when x is 0 and 4, and the time when the velocity equals 0. So A is saying when the instantaneous velocity function, what is the instantaneous velocity function? It's just a derivative. It already kind of labeled that for you. So the velocity's derivative, or you can do f of x with the prime symbol. Okay, so we would go 2 times 5 is 10, x, because the 2 goes to 1, and then minus 3. That's it. So that's all A is asking, is the instantaneous velocity, which we know is just the derivative. The velocity when you're at 0 and 4. So velocity, we know, right, is when we put in the derivative for the velocity is when you put the value into the derivative. So this is going to go 10 times 0 minus 3, which is just -3. So the velocity at 0 is -3. We're not moving velocity. Okay, so then we do the same thing with 4. At 0 seconds, we're negative. We haven't moved. Seems a little like it should just be 0, but okay, then 4, this is a made-up function. So if we put in 4, 40 minus 3 is 37. So the velocity is 37 at 4 seconds. And then C says, what's the velocity, the time when the velocity is 0? So this is the same as the horizontal. It's asking when the velocity is 0. Well, velocity is derivative. So where is the derivative equal to 0? Well, we'd add the 3 over, divide by the 10, and we have 3/10. So at 3/10 time, the velocity is at 0. Okay, that I don't love that equation, but I would like it to be more of 0 is at 0, but what do I know? I don't do physics. I've never even taken physics. I should, just because. Probably help me make sense of a lot more of the physics, but I'm always the business side. Hence the reason I teach your business calc. Okay, 9 is nothing new. Okay, so let's skip 9 just because 9 is just the same thing we've been doing. You can try it if you want. 10's a little bit different. So we have to simplify some of our functions to make them look right to do our derivative. We can't do the derivative of this the way it is until the next chapter, with something called the chain rule, which we don't know yet. So if you go to the tutor center, they're going to be like, use your chain rule. You're going to go, huh? So we can just multiply this out, and then we can use the multiplied, the simplified function, right? So think of this square as 5x minus 6 times 5x minus 6. So times that out, 5 times 5 is 25x squared. 5 times 6 is 30x minus another 30x plus 6 times 6 is 36. So I'm going to multiply it all the way out. Almost done. We can combine our middle terms to be negative 60x plus 36. So we have multiplied that all the way out. Now I can easily take the derivative of that function. Okay. I don't even know if I need to go through the derivative. It's more of just remembering you can simplify things and then do the derivative. Way easier than doing what we call the chain rule later. So 2 times, if I actually finish this, 2 times 25 is 50x minus 60. That's our final derivative. Okay, so simplify and then do your derivative, because it needs to be each term with a plus and minus between them, or you can't. Use our cool shortcut. So the next one's division. If I divide by something, I can write that division under every single term so that it's split up into each term. So I can rewrite this as 8x over x minus 7 over x. So now they're split up, and I can then work with each section. And I can actually simplify this because x over x on the 8 is going to cancel, and I just have 8. Okay, and then minus 7 over x. How can I rewrite 7 over x so that I can easily take the derivative? Well, I've still got the 8, but it's going to be 7x to the negative 1. Bring that x up and make it a negative exponent. The exponent's 1, so it becomes negative 1. Okay, so if you have division, break it up under every single term, or you can't do it. Okay, until we have the quotient rule, which again, next chapter. All right, so if I go to do the derivative, okay, if I go to do the derivative, what's the derivative of 8? 0. It's a number, it goes to 0. And then negative 1 times negative 7 is 7. And then minus 1 more from negative 1 is negative 2. And I could from here rewrite that underneath, right? But I don't have to, but I could rewrite it like this. All right, I hope you love this shortcut, and you can FOIL things out, multiply them out. You can divide and simplify, then use this rule. Square roots become a 1/2, or a third root becomes a third. Exponents x's on the bottom can be moved up, and then use this rule.